name is Ashley Mann, and I'm going to be talking about radicals, which are chemical entities with an odd amount of electrons due to an unpaired electron. When it comes to chemical reactions, we're used to seeing heterolysis, in which a covalent bond is broken and results in a pair of electrons moving to either molecule A or molecule B. This means that one of those molecules gets to keep the pair of electrons from the double bond, and one does not. This transfer is shown using the double-headed arrow that we're all familiar with, which represents the movement of two electrons. Radical reactions are a little different. This is because radical reactions involve the movement of a single electron and involve three different steps. Step 1 is initiation. A radical reaction begins when a covalent bond is broken, which is called hemolytic cleavage. This results in the movement of one electron rather than two. Therefore, each molecule involved keeps one electron, forming two radicals. This is referred to as hemolysis and is shown using a single-headed arrow, which represents the movement of a single electron. A radical has a single, unpaired electron in its outer orbital, resulting in the molecule containing an odd number of electrons total. This makes the molecule unstable and highly reactive because it wants to fulfill its octet. Therefore, it is likely to attack other molecules nearby in its search for electrons. This results in new radicals being formed because no matter what, there will still be a molecule left in the picture with an odd number of electrons. The new radical will then attack another molecule. This is the second step, propagation, and it can occur one or more times. Propagation continues until a radical reacts with another nearby radical, resulting in the two lone electrons becoming an electron pair when they form a covalent bond. This is the third step, and it is called termination. Now that we better understand what a radical is, let's discuss the three major steps of radical reactions in a little more detail. As we've discussed, initiation is the step in which the radicals are initially formed. This is an endothermic reaction and requires a decent amount of energy for the breakage of the bond to occur. In order for this reaction to occur, the bond needs to be broken by UV light, heat, or a metal-containing catalyst. Propagation is the result of the highly unstable and reactive nature of the radical. The radical is desperate to complete its octet and will react with whatever it is around in its hunt for electrons. Various different types of reactions can occur at this step, including addition of a radical to a pi bond, hydrogen abstraction, halogen abstraction, and elimination. All of these result in the formation of a new radical. This step can occur only once, or it can result in a domino effect in which the newly formed radical can go on to attack another molecule, creating another radical, and so on, resulting in this propagation step occurring multiple times. This step of the reaction will occur at least once, but can and is likely to occur many times. As stated, there are three different ways in which a radical can undergo propagation. One of these is addition of a radical to a pi bond. This occurs when an electron from a pi bond forms a covalent bond with a species containing a radical, in this case, a halogen. This results in the other electron from the pi bond remaining on the carbon, creating a carbon radical, adjacent to the carbon bonded to the halogen that was previously a radical. The next two types of propagation are similar. They are hydrogen and halogen abstraction. This occurs when a radical reacts with a hydrogen or a halogen attached to a compound. This creates a bond between the species that was previously a radical and the hydrogen or halogen, but it leaves an odd number of electrons on the compound in which the hydrogen or halogen was previously attached, resulting in that compound becoming a radical. The fourth type of propagation is elimination. Elimination occurs when a double bond is formed and a compound is fragmented into two pieces. In this example, a single electron from carbon 1 bonds with the electron on the carbon radical at carbon 2. This breaks the bond between carbon 1 and the halogen, resulting in a single electron adding on to the halogen as the bond breaks. The result is a newly formed alkene in a halogen radical. Regardless of the type of propagation is likely to occur many times because propagation continues until the radical is in close enough proximity to react with another radical, which brings us to the third step, termination. Termination occurs when two radicals react with each other, forming a covalent bond. This is known as coupling. It is an exothermic reaction because the reactive radicals are excited to react with each other and do not require extra energy to make the reaction occur. Radicals can occur on many atoms and molecules, including carbon. To get a better understanding of radicals, we are going to focus on carbon radicals for a moment. As shown in the photo, carbon radicals are similar to carboanions and carbocations. Like carbocations, carbon radicals are sp2 hybridized and trigonal planar. And like a carboanion, carbon radicals have electrons in the p orbital. But instead of having a pair, carbon radicals only have a single electron. Unlike carbocations and carboanions, though, carbon radicals are neutral. Another way carbon radicals are similar to carbocations is in reference to their stability. The more substituted position the radical is on a carbon chain, the more stable it is, as shown by the graphic. Unlike carbocations, though, radicals do not undergo rearrangements to increase their stability. This concludes my coverage of Introduction to Radicals. I hope you enjoyed it, and I hope you learned something.